Good morning, dear students. I welcome you all students of my MSc final class. As you know, we are discussing the fifth paper, that is condensed matter physics. And in the last video, I started the band structure theory, and I told you about the block theorem, that how we can have a periodic wave function and satisfying a certain condition. Dear students, when we consider a one-dimensional lattice, suppose these are atoms which are arranged at a certain interval, and I confine myself to one dimension only, then you know, due to one nucleus, suppose this is Ze plus, and there is one electron at a distance r from it, then we know the potential energy of the system is given by kZe minus E by R. We all are familiar with it. It is a simple formula, K, Q and Q2 by R. So U is equal to minus kZe square upon R. If I ask you to plot this potential energy, then the graph with suppose the nucleus is considered to be at the origin, then this curve will be there in the fourth quadrant, and it will be like this. R U. This is a graph which you shall obtain. So if I consider, now see, there are so many atoms in the crystal, which is one-dimensional crystal. If I plot these curves for each atom, this is for this on the left hand side it will be like this, for right hand side it will be like this, it is due to third, and so on. See, very interesting result you are going to get soon. Now the superposition of these, this and this, I can show it by a resultant value like this. See, I can show the resultant potential like this between the atoms. So you can see it looks like this, and it is a periodic diagram in which the potential repeats itself with a particular, for example, if I consider this to be, say, x is equal to 0, and then this value is repeated here, and so on. So I can say, if this value is at x and this separation is a, then you will say it will be at x plus a, x plus 2a, x plus 3a. So the period of repetition is a, and the value is repeating itself. Such a potential is called periodic potential. And whenever an electron moves in such a periodic potential, then there can be it is of great interest to solve the Schrodinger equation there. And Kronig and Penney were the two scientists who assumed the one-dimensional crystal's potential to be periodic, no doubt, but they considered a standard shape, that of the rectangular shape like this, that the potential is repeating itself after a certain distance. And then they solved the Schrodinger equation for a moving electron in such a potential, dear students. And what interesting aspect I would like to tell you is that the concept of origin of the energy band came from this model for the first time. We will explain, we will study it rigorously, and I will try to explain it up to the best of my knowledge. So let us start it. This is what the Kronig Penney model states, that in solids the valence electrons are affected by the periodic potential of lattice ions. This is what I told you just before this, that potential of lattice ions. Kronig and Penney considered simple one-dimensional lattice and assumed the periodic potential as simple rectangular potential. This is what I told you, that in actual the potential seems like this, but it, for simplicity, because remember, when you start solving Schrodinger equation, you must know the exact potential form, and this is 1 upon r, but the superposition is no more 1 upon r. So for simplicity they consider it to be equivalent to a rectangular potential. This is what I want to tell you. It is here. The potential can be given as like this. On y direction we are considering the potential, dear students, and along x-axis, say x is equal to 0, the wall of the potential is there. Then from 0 to a, the value of the potential is 0, and then from 0 to minus b, it is plus v0. So what is the period of potential? The period of variation is minus b to a, that is a plus b. So you will see that the same value is obtained here. So period of potential will be a plus b. And I can describe this potential by the mathematical form, that this Vx is 0 here, from in between 0 to a. This is what I have written, x is less than a greater than 0, and then Vx is v0 here when x is less than 0 greater than minus b. One can also write it is the same thing happens from a to a plus b also, but taking 0 as the origin, o as the origin, I can write down from 0 to minus b, it is having a value v0. I will consider the Schrodinger equation, and its solutions will be considered as psi 1 in this region, that I will call the first region, and psi 2 in this region. And you all know in your quantum mechanics that when you solve the Schrodinger equation, then you are dealing with certain boundary conditions, that the wave function must be continuous at the given boundary, its derivative should also be continuous. So we will impose all these conditions here also, and then we will be able to easily solve the problem. This is what I want to tell you. So now I will write down the Schrodinger equation here, and then I will discuss it in continuation. See, the time independent Schrodinger equation for region first and second can be written. What is your first region? Here it is. First region is from 0 to a. So that's why I have written d square psi 1 plus 2me minus 0, because potential is 0 in this region, upon h cross square into psi 1 is equal to 0. This is Schrodinger equation first in the first region, and in the second the potential is v0, so it is 2m upon h cross square e minus v0 psi 2 is equal to 0. This is what we have to. Now I will solve it. I will consider 2m e upon h square as l phi square and 2m e minus